Next part of the paper 2 of unit 2. The key value of the equation, the EQ equation of any nuclear reaction is nothing but analytical relation between the Ke energy of incident and the ejected particle with the nuclear disintegration energy. The nuclear reaction is mostly based on the mass energy conservation, and it is true for all type of reaction. A bombarding particle X hides the target nucleus X, which is at rest. Let Vx be the velocity of the bombarding particle and the velocity of the target nucleus is 0, then Vx is equal to 0. Also mz and mx that are given. We are not going in detail of this equation. Just here to by applying the law of conservation of momentum, mx vx is equal to m gamma v gamma cos phi plus m2 my nu gamma y cos theta, and these equations are there. We are not going in detail of this. They directly q will nothing but the E y in bracket 1 plus my capital My minus Ex in bracket 1 minus mx my. Here this q equation is given. We are not going in detail of such a equation because it is too much bigger equation. What is the Ex and Ey? Ex is nothing but the energy of the bombarding energy, and Ey is the ejected particle energy. That you have to remember. Pi is the angle between the direction. That just terminology we have to remember, but don't worry about these equations. Then general solution for the q equation is given here. Again, just go through this part. It is not that much important as far as the MCQ is concerned. The nuclear reactions are classified energetically into two classes: exorgic reaction and endorgic reaction. Yesterday we have seen that will come for the MCQ purpose of view. Please look on this part. Then the nuclear fission. When the first of all, the uranium was bombarded with the neutrons. It was found that the beta active product that resulted, followed by the whole chain of beta active products, such as here the example. The reaction is given that uranium 238 gives you the 0n1 is which is gives the 92, uranium 239 which gives the 93, X 239 gives the Y 94, 239, etc. It was recognized that more than the one neutron was produced. Vaughan and F. Strassman in 1939 proved that the product might be considered of the two large fragments, which they identify as a barium and a krypton. In 1939, O.R. Frisch and L. Meitner first used the word fission, the process in which a heavy nucleus split into two nuclei of nearly equal parts is called fission reaction. Fission reaction, or say fission reaction, or say you can call it as a fission fragment or the fission fragment. In this process, the neutrons are also emitted with release of the considerable energy. The process in which the heavy nucleus split into the two nuclei of the nearly equal parts is called as the fission reaction, or say fission fragment. Such a types of a process are also observed to occur when heavy nuclei are bombarded with proton, deuteron, alpha particles, even electrons and the gamma rays. Also, further work showed that the lighter elements could also be fission by high energy particles. In this type of reaction, large amount of here the large amount of that particularly uh, in this type of the reaction, large amount of energy is released from the process because the mass of the parent nucleus is greater than the sum of the daughter element produced after the nuclear fission. Reaction and the neutrons are also emitted from this process. The excessive mass emerge out as energy according to Einstein mass energy equation. Example of the nuclear fission reaction using uranium 235 in the thermal reactor as an example. When the neutron is captured, the total energy is distributed amongst the 236 nucleus proton plus nu present in the compound nucleus. This nucleus is relatively unstable and it is likely to be break into the two fragments of around half the masses. This example is there. Okay. This example is the uranium 235 in the thermal reactor. Just that example you have to remember. You can see that uranium 30 ppm give the barium and a krypton, barium plus krypton, zirconium plus tellurium. In such a equation, number of nuclear proton plus neutron is conserved. Example, 235 plus 1 is equal to 141 plus 92 plus 3. Same neutrons will be there. Here this particular fusion reaction is there. Fusion is nothing but a breaking down into the small part. Please, if you are not getting anything, you can ask. Here we will stop. In the next lecture we will talk about the nuclear fusion.